Google has changed its Android runtime code drastically, and based on the user behavior, profiling of data is done for various system level updates, storage, performance, etc. The next talk is going to show you how to steal data in real time from Android 10 ART without execution of code using discompiler or decomposer. Let's invite our next speaker, SungHyoun Song, to deliver his presentation on deep dive into dynamic binary analysis.
Thank you for
SungHyoun is,
yeah
yeah, I was just going
yeah
to introduce you, but you can go
yeah
ahead. You could
yeah.
go ahead.
Thank you for introducing me. Can I share my screen?
Absolutely, go ahead.
Yeah. Okay. Okay. Can you see my screen?
Yes.
Okay. Nice to meet you, everyone. My name is SungHyoun Song. I work at FSI of South Korea. The FSI is responsible the security of Korean financial industry. I am researching mobile security at FSI, and I do penetration testing for Korean financial company. And I have experience speaking at several international security conferences in Europe and Asia. Today, I'd like to analyze how Android runtime works in detail. And based on the analysis result, I'm going to propose a uh, technique to analyze the app easily and effectively by customizing the Android runtime. First of all, I want to explain why I became interested in Android runtime. Analyzing mobile app is a very important process for those who work in mobile security, like malware analysts or hackers. This is because it's possible to get clear idea of how malware works or find vulnerability in your mobile apps only when proper analysis is done beforehand. There are two main ways analyze mobile apps. First, you can analyze the app if it exists as a file. In general, in Android, bytecode can be converted back to the original Java source code using open source tools such as Dextjar. Another way is to analyze the app while the file is executed and loaded in memory. There is a dynamic analysis tool called Frida that can analyze the app during the runtime. Frida is very high-level framework and it's used by almost all security researchers today. So applications that handle sensitive information such as banking, gaming, and healthcare adopt the security technique to protect themselves from the analysis and attacks. We call this technique RASP, Runtime Application Self-Protection. Many security companies develop RASP, make it module, and sell it. And most of apps are sensitive information are actually using the module. These techniques check not only whether the OS has been tampered, but they also encrypted, transmit, or receive data. In addition to that, they detect and block the attackers from accessing the memory area. So if you try to analyze an app protected by RASP, you will be detected and blocked, as shown in picture here. This top picture shows the process of decompiling to the original Java source code using Dextjar. Since the app is protected by anti-decompile technique, you are in trouble with converting it back to the original code. The bottom picture here shows warning message generated when it detects the app running in a rooted environment or any attempt of dynamically analysis using Frida. So can we bypass RASP? Of course. In my thought, there does not exist 100% of security, but what I want is an automated and effective and fast method. However, Security modules are difficult to bypass because they are applied in multi-ways technique. So what's the problem? The problem is time. They also know that the RASP cannot depend completely the attacker. The purpose of the RASP is to annoy the attacker as much as possible and increase the time required for the attack. There is no perfect mechanism, and we are in state of continue to have to fight. I want to get away from the endless fight between protection and bypass, just like Tom and Jerry. So over the past 2 years, I have been thinking about how to analyze the app easily and effectively without being detected by RASP. And I found the two paper published in Usenix 2010 and AMC 2016. The main subject of the paper were about the developing the framework that can dynamically analyze the app by modifying the runtime of Android. It was very interesting as it modified the OS to create an environment for the analysis. The advantage of this technique was that the app could be analyzed without direct access to the app's executable file or memory. But sadly, the paper were written for old Androids, so I had to analyze the new runtime in Android 10 in detail. So I shift my focus from application to Android OS itself, that is kernel and platform. In the past few years, I started analyzing the Android source code and developing the custom OS. So I ended up building the Android OS by customizing the kernel and platform. The OS has built-in functions such as backdoor for privilege escalation, SA Linux bypass, Android verified boot bypass, and kernel memory access driver. I don't think I can cover all of these today due to the limitation of time. So in this session, I will focus the presenting how customizing the runtime for dynamic analysis of app. ART is abbreviation for Android runtime. ART can be called heart of Android and play a key role in app loading app binary, application memory management, app execution, and optimization. However, it is not easy to analyze in deep how the runtime works in the restless version of Android. This is because the size of code is huge, about 100 gigabyte, and various techniques, compiling, profiling, and optimization are also applied to the restless version of ART. In addition, since Google has changed the Android runtime drastically, each time a new version of Android is released to optimize the performance, storage usage, and the system update of apps. How it's structured and how it operates are different from each runtime version. However, since all the code of app is interpreted and executed through the ART, if the attacker understands how exactly the app works on ART, all necessary information can be stored in real time to analyze the app. In this speaking, therefore, aim to analyze Android 10 ART in detail. I propose a new technique to quickly and effectively analyze the app by modifying the ART to divide from the existing app analysis method. I propose a new technique. This technique is not detected by RASP and enable dynamically analysis of all the function executed through the ART. And I also develop a framework in which an attacker can steal code, interface, parameters, return value, field, and stack trace of running function in the real time without using debugger or hooking tool. Let's take a look at how Android runtime has changed from version to version. First, when we talk about Java and Java Virtual Machine, an Android application is written in Java language for developer productivity and code mobility. On desktop and server environment, a Java program is compiled to the Java bytecode, which is an intermediate representation for Java Virtual Machine. JVM run the Java bytecode, and the Java bytecode is based on a stack-based instruction. However, since the performance of stack-based Java bytecode on resource-limited mobile device is poor due to slow interpretation. So Android researchers have created a new bytecode set, which is a dynamic bytecode for dynamic virtual machine to improve the performance of Android application. In contrast, the Java bytecode, dynamic bytecode is based on the register-based instruction set. Therefore, it can reduce the code size and the running time in mobile device. Until Android Pro and earlier, there was only interpreter in dynamic virtual machine. Every time you run app, the interpreter converts all bytecode into native code. It slows down app startup time so badly. In order to boost up the performance, JIT compiler was introduced in Android Pro on dynamic virtual machine. JIT compiler caches the code while generating the native code at the time of execution. To prevent repeated generated of native code for each time of same function call. As frequently used functions are executed with the native code that was created in advance, the performance has increased. These code, however, consume the amount of memory. The runtime structure when JIT and interpreter were in place had not changed for a while. The conventional approach result is very low performance when compared to the compiled language like C and C++. As a result, slow and space constrained computing device have tended not to include virtual machine. So Android KitKat, Google introduced a new runtime, AERT. In Android KitKat, AERT was experimentally available. Starting from Android Lollipop in 2015, Google decided to replace dynamic virtual machine and made AERT as the default runtime to improve the runtime performance. AERT adopted ahead of time compilation strategy instead of interpretation. AERT provides compiler called DEX208. The DEX208 will directly compile DEX bytecode into native code during app installation and then stored as an AOT file. The result is essentially an ERF file that is then executed natively. So instead of having bytecode that is interpreting by virtual machine, it now has native code that can execute natively by the processor. This is called AOT compilation. But main difference is AERT precompiles everything. But dynamic virtual machine use heuristic to detect the code that runs most often and only compile the subset of bytecode during execution. And another difference between old deep dynamic virtual machine and AERT was the performance. As all execution code of app were ran as native code, the startup speed was improved compared to the bytecode. In addition to that, every time you ran the app, it didn't use an interpreter, but it called the native code, and it resulted in reducing battery consumption. Since JIT was used anymore, the memory usage was also reduced because it didn't keep the code cache memory. And AOT compilation to DEX to OAT compiler can perform multiple passes for optimization to achieve a better performance. But it lost as much as it gained. The biggest problem was it took too much time to install apps, and it took too much time to update the system via OTA. Eventually, by compiling all bytecode to native code at app install time, it gained the app's performance. However, it required more time to update apps and system, and more storage too. Then it is really best to compile all bytecode into native code at app install time. We need to first understand the usage pattern of mobile users. In fact, we don't use all menus in the app. For example, I use the mobile banking app. There are a lot of financial related menu in the app. And I use just two menu. First, I check how much in my account. Second, I transfer money from the account. That's it. Although there are so many menus in the app, I use only two features. Then you don't really need to compile everything, wasting your time and storage. All you need is selectively compile the code that is frequently used by users. So in Android 7, Google was reintroduced the just-in-time compiler that was removed in Android 5. The JIT compiler complements AOT compiler and help improve runtime performance. And they removed the bytecode compiling step in AOT compilation during the app installation. So when will the AOT compiler start working? Google introduced a new technique called profile guide optimization. During the app installation, the AOT compiler does not operate, and the app is installed immediately as bytecode. When you use the app, the bytecode is executed using the interpreter, and it counts how many times each individual function is called at execution time. As the number of execution increases, it divides a state of function from cold to warm and finally hot. Once the state of function becomes warm, profiling info is created to record the information such as a number of execution, then save in the mobile device. When you don't use your phone or when you charge it, based on the profiling info, the profile service uses AOT to compile to the bytecode into native code and store it. And once the state of function reaches hot, the bytecode is compiled into native code by JIT compiler and stored in memory as a cache. I explained earlier, and the old compilation method convert all bytecode into native code and stored regardless of the usage pattern. It rarely slow down the update and installation and required more space. But now we have profile guided optimization that selectively create a native code for the feature frequently used. Profile guide optimization allows the Android runtime to help improve the app's performance by building a profile of the app's hot code and focusing each optimization. It leads to big improvement while reducing the traditional memory and the storage impact of a fully compiled app. It seems we found the perfect balance between app speed, storage usage, and the update time. However, sadly, this method turned out bring another problem. So, what's problem here? However, app run slow at first launch because Profile guide optimization rely on the device to optimize app based on this code profile in idle time, which means it could be a few days before the app to run faster. To solve the problem of slow execution at first launch of app, Google introduced cloud-based profile technique in Android 9. As shown in figure, the profile information of app created on each user's device is uploaded to the cloud server. The cloud server most app share good amount of code profiling information that are used across of different users and device, and these can be globally optimized for everyone. The initial user's device can create profile information for rest of the user space. So the following users can optimize the app after AOT compilation using cloud-based profile data at the time of app installation. This slide shows the whole process of how apps are compiled and executed in Android 10. First, when you try to install app, APK file downloaded to your mobile device along with optimized profile data, as I described earlier. During the installation, the profile information is used by AOT compiler to selectively compile the bytecode into AOT code. For the function are commonly used by users. Second, when you executed app, ART checked whether the code of the running method is compiled or not. If the code is already compiled by JIT or AOT, it directly called the code loaded in memory and executed it immediately. If the code is still bytecode, the interpreter executed it and increased the method execution counter. If the counter of the method continued to increase and it become warm state, the profile information, such as the number of method execution, is saved in the device as a file. While you are not using the phone, just charging overnight, the service compiled the warm method using AOT compiler and save it in file as AOT code. Next time, method will be executed right away as AOT code from beginning. And if the counter keep increasing and it finally become hot state, the method is compiled in the real time by JIT compiler and stored in memory as code cache. Then the code loaded in memory is executed as soon as function is called. As you can see here, ART's various state of code and complex structure where the app are optimized and executed based on the pattern of the individual and entire user base. Okay, now I'd like to take a closer look at the Android runtime at the code level. Based on that, I'm going to propose a technique to analyze the execution of app through the ART customization. As we saw earlier, there are three types of code in ART. The basic text code, compiled AOT code, and the JIT code. AOT code and byte code are saved in the file, while JIT code exists in memory as a cache code. In mobile device, there are three files in application directory that store the AOT code and bytecode information. The first one is base ART. The file contains ART internal representation of some strings and classes list in APK, used to boost up application startup time. The second one is base ODEX file. The file contains AOT compiled code for method in APK. The rest one is base VDEX file. This file contains DEX code in APK with some additional metadata to speed up verification. These files can be dumped to DEX bytecode and AOT code using OAT dump module. These pictures show the result of dumping the base ODEX file stored in application directory. If we look at the first line in blue, there is the init function as first method in the class, and the name is com apps flyer internal AC. This init function exists in two different forms. The part written as DEX code is a bytecode of init function. The second part is written code is compiled code, which was converted from bytecode into AOT compiler. And if you look at another part, you can see init function in class com apps flyer internal $1. This function has DEX code, but the code area just show no code. It has no compiled code, but it exists only as bytecode. So what does it mean? Even if the function converted and saved into the compiled code by AOT compiler, the bytecode is saved anyway. This is because the original bytecode is used when debugging is required or ART update to re-optimize the code in the app. If so, let's take at how bytecode and AOT code are loaded into memory by ART. Each code linked to ART method object through the class linker. The ART method object is instantiated object in the form of C++ class to execute each method within the Java class on ART. Base ODEX file contains the OAT code and base VDEX file contains the byte code. When the app is executed, each file loaded into memory by runtime. This is a simplified picture how AOT and bytecode are linked to ART method object inside the ART through the class linker. Before the execution, all methods in the app are linked to the execution code are as ART method object. The class linker called the function set entry point from quick compiled code to assign the address of AOT code to the entry point from quick compiled code variable of ART method object. And by calling set declaring class function, text cache is assigned the declaring class variable of ART method object. Now we can call the bytecode through the DEX cache. In short, all functions executed by ART are loaded into each ART method object. We can execute function through this object. As we saw here, there are more than one type of code we want to execute. So we need to call different type of code for bytecode and compiled code. As shown in the picture, one main function consists of several sub-functions, and each sub-function also consists of several smaller sub-functions. Let's take a look at the step to call the execute sub-function 232, main function, and sub-function 2, sub-function 23, sub-function 232 are called in that order. Each function exists partially as bytecode and partially compiled code. Because of that, we need to call the compiled code from bytecode and bytecode from the compiled code. This cross-call from different code make ART structure more complicated. So let's see how ART cross-call the different code. The first code execution is started from the ART method. This is because the ART method object both bytecode and compiled code. If the function exists as a compiled code, ART directly invoked the code and executed it. If the compiled code doesn't exist, the interpreter is used to execute the bytecode of the function. And after the execution of different type of function, the compiled code call the interpreter, or vice versa. Sometimes the interpreter call the interpreter again. In this way, state changing occur frequently within the ART structure. This is a code flow that analyzes the execution process in ART. Here, compiled code called the bytecode, and bytecode called the compiled code, and bytecode also called bytecode. I think it may not be easy to understand the whole process at once, but if you focus on the code execution aspect, there are two parts in the whole picture where code is executed. The first part is compiled code, which called ART quick invoke stop function through the invoke function in ART method. This function invoke and executed the compiled code. The second part is the bytecode, which called executed mtrp impl or execute switch impl function through the interpreter's execution function. This function converts bytecode into native code and executed it. All the information required to execute app go through these two parts. The information contains part, parameter, and written value, and code, call stack, and so on. In other words, if you watch ART method invoke and interpreter execute function, you can trace all the code running on Android. Is that really possible? However, there was one missing piece, the piecing that we could not see in the flow. What is that? That is the process which compiled code called the compiled code. So why this code not shown in the picture? I'd like to go back to remind you how compiled code is called. As I explained before, ART method invoke the core ART quick invoke stop function to execute compiled code by invoke the code loaded in memory. Let's dig into more about this part. The invoke function of ART method class called the ART quick invoke sub function. The ART quick invoke sub function is written in ARM assembly code to boost up the execution speed. This function has address of target function to be invoked and executed. This picture shows the code get the address of function to be executed. This part contains the address of variable, entry point from quick compiled code, and this variable contains the address of the compiled code for the executing function. Put this address into X9 and directly call the compiled code using branch instruction. Let's call this compiled code A, then A directly call the address of next function B, which is in compiled code. Again, B directly call the address of next function C, which also exists in compiled code. Unlike the call structure we saw before, we can see the directly call from memory to memory when compiled code called another compiled code. If this is the case, it's impossible to trace the code when compiled code is executed from the compiled code. In addition, since the compiled code has been optimized a lot of compared to the existing Java code, it's tricky to extract the original code even if you access the compiled code. So what I did is to change the core structure. So bytecode was always called instead of compiled code for target function. So I changed the ART method invoke function to stop executed compiled code and instead use the interpreter to execute bytecode. In this method, ART method invoke function to execute compiled code in the existing flow is not called. Instead, it forced to always call the bytecode using interpreter. This allows you to trace the flow or function because they are all executed using interpreter. Furthermore, you can get the original code more easily because the execution code you are getting in smali code format. For this purpose, I customize ART display all information by adding the trace feature to two functions, ART method invoke and interpreter execute. As shown here, no matter whether there is compiled code for the function to be executed in ART, it will eventually call bytecode. This feature is table comparing is Stacktrace before and after code flow change in ART with the technique introduced in this speaking. This feature is divided into two results. The above is Stacktrace result before changing core structure, and the bottom is result from Stacktrace after the change. Before change, the function that exists compiled code were called from function that exists compiled code. In this case, it was impossible to trace all function. In the result of Stacktrace of changed structure, the compiled code cannot be executed in the ART method invoke function, and the bytecode is executed by calling interpreter. This chapter introduced the framework developed with the previous described technique. I have no time, so skip this and I display demo. Right is Ubuntu console screen, and left is phone mirroring screen. The app is analyze Santander used in Argentina. And first, open the configuration file on mobile device. Here is target app UID, stack trace option, code dump option, ARG info option, and include and exclude option. First, you get the UID of target app. Target app UID is 10, 16. Target app UID is 10, 16, and 8. Then start the app. You can see all functions executed in ART. Too many functions are executed, and you can save it as a log and analyze it later. Second, you will add an option, remove the default Android function. Second, you will add an option, remove the default Android function. You will only see the custom function. You will see only custom functions. The amount of function display is much smaller than before. And then choose a few functions that you want to analyze in detail. I select com indra blah blah function. You only need to then you can see the com indra class in the log. And choose another function you want to analyze in detail. AR com Santander. And you can see the parameter and return value. You can see the parameter and return value. You can see the credential data. And you can see the encrypt function. Finally, I choose another function, AR com Santander Rio and banking crypto blah blah. We can see plain text with crypto data easily. Then set the stack trace option. You can see the stack trace of the target function. And you can see the dump code, smali format. You can see the private key. In conclusion, I developed a new analysis environment by analyzing and modifying the structure of ART. This method is very easy and effective and powerful. Thank you for listening. If you have any question, please contact us on Twitter or email. Thank you.